Hello everybody and welcome to the top of page 56 in the workbook. In this video we are going to be proving part 3 of the long cosets lemma from the previous page, 55. Just so we don't have to flip pages, I went ahead and wrote down the statement of 3. And before we prove this, let's remind ourselves what this was telling us. Okay, so this was a statement about the behavior of cosets, and in particular it tells us that given any two cosets that you might calculate, there are exactly two possibilities. Either the cosets are exactly equal to each other, or they're completely disjoint from each other. Okay, so this was the property that's guaranteeing that the cosets will always partition our group, whatever it is. All right, so let's take a look at how we might prove this. Turns out that a cases argument works really nice for this. Okay, so I'd like to start with the case that AH and BH are disjoint. Okay, if we assume that, notice that that's exactly one of the two parts of the statement that we're trying to prove. So if we start with that assumption, we're done in one step, okay, because we already have the fact that AH and BH are disjoint. So you can think of case 1 as being kind of a trivial case. Okay, just making the observation that if that were true, we'd be done already. And then ask ourselves, what's the other possibility? Well, if AH and BH are not equal to the empty set, then they have to have an element in common. Okay, so if that intersection is not empty, then we can choose an element that's in both of those cosets. So we'll start by doing that. And then remind ourselves what that would mean. Okay, that's saying that x is in AH and it's in BH. The fact that x is in AH just means that we can write x as A times something that's in H. And the fact that it's in BH tells us we can write x as B times something that's in H. Okay, where these H1 and H2 are just some elements in H. Okay, and this is going to turn out to be an important equality, so I'm going to give it a name. We'll call it star. Okay, now where are we going with this? Okay, well, what we're going to do is to show that the first part of this OR statement is true. Okay, if we can show that, then we've shown the either or statement. So I'm just going to sneak that in here. We'd like to show that AH equals BH. Okay, and because what we're trying to do is to show that two sets are equal, we'll just use a standard pick-a-point argument here. Okay, so take any y in AH, the set on the left-hand side. Remember what that means again. Saying that y is in the coset AH just means that we can write y as A times some element H that's in our subgroup. Okay, for some little h in the subgroup H. Okay, and then what we're going to do is to go back to equation star, just make a couple of observations here. Okay, and in particular, I want to focus on the part of star that says that A times H1 equals B times H2. We can take that equation and actually solve it for the variable A by multiplying both sides on the right by H1 inverse. So that means that A is going to look like BH2 times H1 inverse. Okay, again, that just comes from this equality here that I'm underlining. Okay, so since that's true, we can notice the following here. So y is equal to A times H. Okay, but A is also equal to BH2 H1 inverse. Okay, so we can substitute that in for A. And then do a little grouping here. That's B times H2 H1 inverse times H, but what do we know about this element that I'm underlining here? We're taking a product of three elements that have to be in H, and H is a subgroup, so that means that that product that I underlined has to be in H, and so by definition, we've just demonstrated that this y is in the coset B times H. Okay, but if you look at where we started and where we stopped, we took a y in AH, we demonstrated that it's also in BH, we have shown then that AH is a subset of BH. Okay, and remember what we wanted to show was that the two sets are equal to each other. We're halfway there, and I'm just going to make a comment that a very similar argument would prove the reverse inequality. You can try that part yourself. Or I'm sorry, the reverse containment. Okay, similar argument shows that BH is a subset of AH, and that would complete the proof that AH and BH are really the same sets. Okay, so we have just proved the fact that the cosets partition our group.